So basically, a sequential circuit will where your output depends upon your present state as well as your past inputs also. Okay. So in the case of your sequential circuits, your output is dependent upon both present input as well as your past input. Whereas in the case of combinational circuits, your output is only dependent upon your present inputs. It is not dependent upon your past inputs, and it will not remember any past inputs. Okay. Whereas in the case of sequential circuits, you have a memory element so that you can remember your past inputs also. Okay. In the case of sequential circuits, your output is dependent upon the past inputs as well as the present inputs. So basically, the sequential circuits are divided into two types. One is synchronous sequential circuits. One is synchronous sequential circuits, and other is known as asynchronous sequential circuits. So one is known as your synchronous sequential circuits, and another is known as asynchronous sequential circuits. So what do you mean by synchronous sequential circuits? Synchronous sequential circuits are nothing but which responds to the inputs only at discrete time intervals. Okay, so here it will only respond, it responds to the inputs at discrete time intervals. Whereas in the case of your asynchronous sequential circuits, your output is immediately responds to the input level changes. It will immediately respond, immediately, or the circuit will immediately respond to the input level changes. So this is nothing but your sequential circuits and this is nothing but your synchronous sequential circuits and asynchronous sequential circuits. Now, so for example, let's see one asynchronous sequential circuit. So your asynchronous sequential circuit. So how it is going to look like your asynchronous sequential circuit? So your sequential circuits will also have one combinational logic. It will have one combinational logic where you are going to apply your input here and you're going to get your output. That is common, and there will be one feedback. So your output will be given and there will be one memory element. So this output is given to one memory element, and from this it is given feedback to again to your input. And this circuit which I have drawn is asynchronous in nature. That is, your output will immediately change with respect to the input. Your circuit will immediately respond to the whatever the values which your input is being given. Okay, so this is asynchronous sequential circuit. Whereas in the case of synchronous sequential circuit, you have one control signal like clock or enable. Okay, so I will draw that. Come into your synchronous sequential circuit, you will have control over your circuit. Okay, so this is your sequential circuit. So whatever the circuit which you have drawn here, so this whole circuit I am considering it as a simple sequential circuit. Okay, that I have drawn here. Okay, which has one input. Inside the sequential circuit only, if you elaborate, you will have one combination logic with one feedback. Okay, so instead of drawing that, I have made it a block. Okay, and followed by output, and your circuit will have a control signal like clock or enable. Then this is nothing but your synchronous sequential circuit, where your circuit will respond to the inputs only at discrete time intervals or at the passage or negate or level sensitive or edge sensitive. These are all we have. Okay, so this is nothing but our synchronous sequential circuit. Is this clear? The synchronous sequential circuit and asynchronous sequential. So let's say if we have a single NOT gate. Okay, let's say if we have a single NOT gate like this, if we apply A here, you are going to get A bar. Like let's say suppose if you are applying 0, you will get 1. And if you apply 1, you will get 0. This we already know. Now, let's say if you are having a NOT gate connected to one more NOT gate in series. Okay. Now, if you apply A here, you are going to get A bar, and again you are going to get A. That is, if you are applying 0, you are getting 1 and again 0. And if you are applying 1, and here you are getting 0, and again you are getting 1. So that means this particular circuit is holding your data. This particular circuit is holding your data for some amount of time. You can see here. Okay, so if you apply 0, let's say we have some propagation delays in between. Okay, let's say this propagation delay is 2 nanosecond, this propagation delay is some 2 nanosecond. So for 4 nanosecond, after 4 nanosecond, you are getting the same data output. That means this particular circuit is holding your data. So using these two NOT gates which are connected in series, you can construct a basic memory element. Okay, and let's say if I am drawing this circuit like this, one NOT gate and one more NOT gate, and this NOT gate feedback is given to your first NOT gate, then this will become a basic memory element. Like let's say suppose the initial value of this is 1, then it will become 0, and again this is being repeated. So continuously it is storing by this particular feedback. Okay, so it is continuously storing this particular value 0. Okay, and I can rearrange this particular circuit like this. This is one NOT gate, and this is one more NOT gate, and this output is given to this one, and this output is given to here. So this is a basic memory element you can build using your NOT gate. Is this clear? Yeah. So using this NOT gate, you will have only one inputs. Okay. So that's why we are going to NOR and NAND gate for building our basic memory elements, so that we can store our data and we can have more than one inputs. Okay. So what are the gates which we can use for replicating this NOT gates? We can use NAND gates and NOR gates. Okay. So we have basically latches and flip-flops. So these are your basic memory elements which can hold the data. Okay. So basically latches are level sensitive devices, level sensitive, and whereas your flip-flops are edge sensitive devices. And please don't give your answer as latches don't have clock and flip-flops will have clock. Okay, so that's not correct answer. So latches are level sensitive and flip-flops are edge sensitive. Okay, and basically your yeah, so basically your latches are level sensitive and flip-flops are edge sensitive. Okay, so this is the main difference between your latches and flip-flops. We will discuss what do you mean by latch and what do you mean by flip-flop. Okay, so first in the latches we have SR latch, JK, D, and T. So SR latch, JK latch, and D latch, and T latch. Whereas in the flip flops also we have SR, JK, T, and D. Okay. So let us first try to understand what do you mean by latch. So this latch, it is a basic memory element. It is a simple basic memory element. Okay. So let us see one basic latch like RS latch. Okay. With the help of your NOR gates. So how to build this RS latch using NOR gates? We can take two NOR gates. Okay. So this will be given here, and this is your, and this will be given here. Okay, so this input is given from this output, and this input is given from taken from this output, and this is nothing but our R. I will write down here. So this is nothing but our R, and this is nothing but our S, and this is Qn output, and this is Qn complement. Okay, so this is nothing but our RS latch using NOR gates. Okay, let us try to understand what happens if R is equal to 0, S is equal to 0. Let us try to analyze. So if your R is equal to 0 and S is equal to 0, that means your Qn is nothing but, you can substitute here. I will write down here. So if R is equal to 0 and S is equal to 0, 0 and 0. Now let's say our initial value of your Qn is equal to 0 and Qn bar is equal to 1. Okay, that means we have here 1. So 1 plus 0 is 1, and the complement of that is nothing but 0. So the Qn will be still 0, and this 0 will be passed over here, that is 0 plus 0, that is 1. So if your R is equal to 0 and S is equal to 0, you are getting still 0 and 0. So R is equal to 0 and S is equal to 0 if Qn is equal to 0. Here Qn is nothing but our present state. And we have one more term here, that is Qn plus 1. That means it is next state. It is nothing but 0. Okay. Now, so this is one combination. Now let's say if your R is equal to 1 and S is still 0. So if any one of the input is let me use one more color. So here R is equal to 1, we are changing it to 1, and here also we have 1. So since R is equal to 1, that is 1 plus 1, that is nothing but Qn is equal to 0. So this 0 will be transferred over this particular gate. So it is 0. Now this 0 and we have S is equal to 0. So Qn bar is still 1. So if R is equal to 1 and S is equal to 0, still we are getting Qn is equal to 0 and Qn bar as 1. Okay, so I'll write down here. So R is equal to 0, sorry, R is equal to 1 and S is equal to 0. Then if our present state is equal to 0, and then our next state will be equal to 0 itself. Now let's say if your R is equal to 0 and S is equal to 1. R is equal to 0 and S is equal to 1. That means one of the NOR gate input is 1. Then obviously your output will be equal to 0. Okay. So this 0 will be transferred over here. Okay. We have one more 0. So that means 0 NOR with 0, that is nothing but 1. So if R is equal to 0 and S is equal to 1, we have our output as Qn is equal to 1 and Qn bar is equal to 0. I will write down here. So R is equal to 0 and S is equal to 1. And what is the present state we have taken? Qn is equal to 0. Then our next state is simply Qn plus 1 is equal to 1. Okay, so this is one condition we have seen. And coming to the last condition, let me erase this. So coming to the last condition, what is the last condition we have? R is equal to 1 and S is equal to 1. So any one of the input of your NOR gate is 1, then simply your output will be equal to, it will be equal to 0. Okay. And here S is equal to 0, then here 0 plus 1, that is 0. So we can see Qn is equal to 0 and Qn bar is equal to 0. So Qn is 0 and its complement is also 0. Is this valid or invalid? So any number complement is also the same number. It is valid or invalid? It's invalid. Okay, obviously it's invalid. So R is equal to 1 and S is equal to 1. If your Qn is equal to 0, then Qn plus 1 is 0 and Qn plus 1 bar is also equal to 0, which is invalid. Which is invalid. So this is how your RS latch is basically working. Okay. So whenever your R is equal to 0 and S is equal to 0, your present state and next state are equal. Okay. And let's see one more scenario where R is equal to 1, S is equal to 0 and Qn is equal to 1. Let us see what is Qn plus 1. Okay. So let me erase this. So here R is equal to 1, S is equal to 0, Qn initial value is equal to 1 and that is Qn bar is equal to 0. So this 0 will be transferred over here. So any one of the your NOR gate input is 1, then obviously your output will be equal to 0. So it is changing to 0. So this 0 will be transferred over here and this Qn bar will become 1. So from here we can see that whenever your R is equal to 1, whatever may be your present state, your next state is always equal to 0. Your next state is always equal to 0. Okay. And in this case also you can check where your R is equal to 0 and S is equal to 1, your present state is equal to 0, we have checked it. And you can also check whenever your R is equal to 0, S is equal to 1, if your Qn is equal to 1, what is your next state? So we will get 1 only. So from this discussion, we can draw the truth table of this particular RS latch like this, where your inputs are R, S, and your present state is Qn, and your next state is Qn plus 1. So this is the truth table of your RS latch, where your inputs are 0, 0, and your present state is 0. Whenever your inputs are 0, 0, and if your present state is 1. This is one condition. And whenever your present states r is equal to 0 and s is equal to 1, and if qn is equal to 0, this is one condition, 0 1 and 1, this is one more condition. Okay, and 1 0 0 1 0 1, this is last one more condition, and 1 1 1 1 0 and 0, this is one more sorry 0 and 1, this is one more condition. Okay, so for the first one, whenever your r is equal to 0 and s is equal to 0, whenever your r is equal to 0, s is equal to 0 and qn is equal to 0, so you are getting the same value as 0 only. Okay, and whenever your r is equal to 0 and s is equal to 0 and your qn is equal to 1, where is this condition which we have written? Okay, we haven't checked up. Okay, but if you check, you will get the same one only. That is nothing but 1. So this is nothing but hold state or latch condition. That is whatever the input is present, you are getting the same output. That is whatever the present state you are having, then the next state also you are having the same. Okay, and whenever your r is equal to 0 and s is equal to 1, whatever may be the present state, your next state is equal to 1. It may be, if it is 0, the next state will be equal to 1, and if a present state is 1, next state will be 1 only, because your s is equal to 0. This is nothing but our set state. This is nothing but our set state. And whenever your r is equal to 1, whatever may be your value of present state, you are getting your next state as 0. So this is nothing but our reset state. And these two are our invalid states. So I'm going to write don't case here. So this is nothing but our RS latch. Is this clear? RS latch, is it clear? So this is our RS latch. Now we have developed this RS latch using our NOR gates. Okay, let us try to develop our RS latch using our NAND gates. So RS latch using NAND gates. So how to build this? Same procedure. So this is our NAND gate, and this is one more NAND gate, and the input for this is given from this output, and the input for this is given from this output. Okay, and this is our S and this is our R. So for RS latch using NOR gates, you are going to give R here and S here, and for the RS latch using NAND gates, you are going to give S here and R here. Okay, so here you should be careful, and this is Qn and Qn bar. Okay, now again we will take the same conditions where your S is equal to 0, R is equal to 0, and if your Qn is equal to 0, what is your Qn plus 1? Okay, and if your S is equal to 0, R is equal to 0, and if your Qn is equal to 1, what is your Qn plus 1? For this we will see the two conditions, and for S is equal to 0, R is equal to 1, and if your Qn is equal to 0, what is your Qn plus 1? Let us see. And whenever your S is equal to 1, R is equal to 0, and if your Qn is equal to 1, what is your Qn plus 1? Let us see. And whenever your S is equal to 1, R is equal to 1, if your Qn is equal to 0, then what is your Qn plus 1? Let us try to understand these cases. Okay, so first of all, let us see the first case, whenever your S is equal to 0 and R is equal to 0. Okay, so apply 0 and 0 here. Okay, so obviously if you give any one of the input of your NAND gate as 0, you are getting your output as 1. And what is the initial value of Qn? It is 0, so it is changing to 1. And here also it is changing from what is the initial value? So here the initial value is 1, and it is changing to 1 itself. So your Qn is 1 and Qn bar is 1. So is it valid or invalid? So whenever your Qn is 0 and Qn bar is 1, Qn is 1 and Qn bar is 1, it's an invalid. Okay, so here you are getting 1 and Qn plus 1 bar also you are getting as 1. So this is invalid. And okay, and S is equal to 0, R is equal to 0, whenever your Qn is 1 also you are getting, let's see, whenever your Qn is 1, it is changing to 1 itself. And if it, okay, let's see. So let me erase this. So what is the initial value of Qn? Initial value of Qn is equal to 1. Okay. And what is the initial value of Qn bar? It is equal to 0. Okay. So this 0 will be transferred over here. That means your NAND gate output is still 1 itself. And this 1 will be transferred over here and still it is 1 itself. So again you are getting 1 and 1. So this is again invalid. Okay. This is again invalid. Qn plus 1 bar is equal to 1. So this whole case is invalid. So whenever your S is equal to 0 and R is equal to 0, it is an invalid case. Okay. Now, so whenever your S is equal to 0, R is equal to 1, let us see this case. S is equal to 0, R is equal to 1. Let me erase this. Whenever our S is equal to 0 and R is equal to 1, S is equal to 0 and R is equal to 1. So obviously one of the input of your NAND gate is equal to 0, your output will become initial value of your Qn is equal to 0. So it will become 1. Okay, and here you have 1 and we have 1 here. So 1 and 1 and with 1 is nothing but it is 0. So initial value of Qn bar is 1 and it is becoming to 0. So whenever your S is equal to 0 and R is equal to 1, Qn is equal to 1 and Qn bar is equal to 0. So the Qn is equal to 0, then your Qn plus 1 is nothing but it is 1. Okay. Now, whenever your S is equal to 1 and R is equal to 0, let us see this case. S is equal to 1 and R is equal to 0. So here we have 0. That means obviously the Qn plus 1. Okay, let me erase this. So whenever your S is equal to 1 and R is equal to 0, that means here it will become, initially it is 1 and again it will be 1 only. And this 1 will be transferred over here, and 1 NAND with 1 is nothing but 0. Initially it is 0 and next state will also be equal to 0. Okay. So whenever your S is equal to 1 and R is equal to 0, if your present state is equal to 0, okay, we have taken 1 now. Okay, if we taken 1, let us see. So S is equal to 1, R is equal to 0. Our present state we have taken as 1 and this is nothing but 0. Now this 1 will be transferred over here, that is 1 NAND with 0, that is nothing but 1. Okay, Qn bar is nothing but 1. And this 1 will be transferred over here, this will become 0. Okay. So from this analysis we can say that whatever may be the value of your Qn, whatever may be your present state value, whenever your S is equal to 1 and R is equal to 0, your next state will be equal to 0 only. Okay. Now, whenever your S is equal to 1 and R is equal to 1, S is equal to 1 and R is equal to 1, the final case, let us see and let us come to the conclusion. So, whenever your S is equal to 1 and R is equal to 1, what is the present state? I have taken 0. Okay. So, it is nothing but 0 and this is 1. Okay. So, this 0 will be transferred over here, that is, it will be 1 itself. And this 1 will be transferred over here and this will be 0 itself. So whenever your S is equal to 1 and R is equal to 1, your present state and next state both are same. Both are same. Now, what is the conclusion from this? So what do you see from this? So here we can see this SR latch using NAND gate is exactly opposite to your SR latch using NOR gate. Okay, so this SR latch using NAND gate is exactly opposite to your SR latch using NAND gate. Okay, so let me draw the truth table for this. S R Qn and Qn plus 1. S R Qn Qn plus 1. 0 0 0 0 1 0 1 0. This is one case we have, and 0 1 1. This is one more case, and 1 0 0 1 0 1. This is one more case, and 1 1 1 1 0 1. Okay, so these two are invalid states. Okay, and this is nothing but 0 1, that is set. Say S is equal to 0, R is equal to 1, set state, and S is equal to 1, R is equal to 0, reset, and this is hold. So this is your set, sorry, this is invalid, set, reset, and hold condition. So you can say this particular latch is nothing but active low latch. And the latch which we have drawn using this NOR gates, this is nothing but our active high latch. So this is how you are going to draw active high SR latch and active low SR latch. So is this clear? Any doubts or any questions? Do you find any disadvantage in this particular latch diagram? Or do you find any disadvantages in this particular latch circuitry? Now, first of all, tell me, is this synchronous or asynchronous? Asynchronous in nature. Whether it is synchronous or asynchronous. Exactly. This is asynchronous. Why? There is no control signal. Your circuit is responding as soon as you are giving your inputs. Yes. So the circuit which we have seen here is an asynchronous. So the circuit which we have seen here is an asynchronous circuit where your circuit is responding continuously to your inputs. Okay. So there is no control over here. Okay. So for giving control over this particular circuit, for getting the control over this particular circuit, we are going to another type of circuits which are known as gated latches. Okay, gated SR latch. So let us see what is this. So what is happening here is because of its asynchronous in nature, whenever there is some noise in your input, whenever there is some noise in the input, that will definitely affect your output. Okay. So there should be some controlling mechanism so that the circuit will not be active for whole time. Okay, so that's why we are going to another type of latches which are known as gated SR latch. Okay, so how your gated SR latch is going to look like? So it is going to have one control signal. Let's say it is as enable. So whenever your enable signal is high, then only your latch will work, or else your latch will not work and it will hold the previous state itself. Okay, so let me draw the gated SR latch, gated SR active high latch. So first of all, let me draw the truth table for this. So enable S R Qn plus 1. So whenever your enable is equal to 0 and whatever your values of S and R, your present state, whatever may be the value of your present state, okay, so it will be same only. Qn plus 1 is nothing but Qn only. Okay, and whenever your enable is equal to 1, then only your latch is going to work. Whenever S is equal to 0, R is equal to 1, and if Qn is equal to 0, Qn plus 1 is 0. 1 0 1 1 0 and 1 1 0, if it is 0 1, and 1 1 0 1 1. So whatever the table which we have seen, the same table which we are going to draw here, but one thing we should be careful here is the enable signal. Whenever your enable signal is 1 only, then only your latch is going to work, or else your latch is not going to work. Okay, it is going to hold the previous state. Now let us see the diagram for this. So the same gated SR latch using NOR gates, let us see first. So this is your NOR gates. And this input will be fed from this output, and this input will be fed from this output, and this is your inputs. So what we have done, we have simply given taken this, right? So now we are going to use our AND gates here and here. So we are going to use this AND gates, and this AND gates are fed with one input as R and another input as S. Okay, and one more input of this two AND gates is fed with one signal which is known as enable. So whenever your enable is equal to 1, then only the output of this AND gate will be given. Whenever your enable is equal to 0, this AND gate will be off. Okay, and the output will be 0 only. Okay, so this is how you are going to work. So for example, whenever your enable is equal to 0, that is this output is 0 and this output is equal to 0. That means R is equal to 0 and S is equal to 0. That means this is nothing but our hold state. Okay, but whenever your enable is equal to 1 and whatever the value of R you are going to give and whatever the value of S you are going to give, accordingly it is going to work as your normal SR latch. Okay, but if your enable is equal to 0, your latch is off, turned off, and it is going to hold your previous state values only. Okay, so this is nothing but our gated SR latch. Is it clear? Gated SR latch, is it clear? And the enable signal which we are using, so this particular gated SR latch is a level sensitive device. Okay, so this gated SR latch, it's a level sensitive device. So why it is a level sensitive device and what is meant by level sensitive device? Let us try to understand. Let's say suppose this is our enable signal. It is becoming 0 and somewhere it is becoming high again and it is becoming 0 and becoming again high. Okay, and this is our S, R and Qn and okay Qn, and let's say our S is equal to 1 here and it is becoming 0 and again it is becoming 1, becoming 0 again and again it is 0, it is becoming 1 over here, and coming to R it is equal to 0 and it is becoming high here and again it is becoming high and it is becoming 0. Okay, so this is the timing diagram of our gated SR latch using NOR gates. Okay, and coming to your QN, how your QN is going to look like. Let's say initially your QN is equal to 0. Now when is your latch going to sample your S and R? Whenever your enable is equal to high. Okay, so during this time, whenever your enable is equal to high, during this level, during this whole level your SR latch will be high. Okay, and during this negative level or low level your SR latch is not at all active, and whatever the value of S and R you are going to give, it is not going to consider those. Okay, so in this negative level or low level it is off, your SR latch is off, and this in this high level your SR latch is on. Okay, so during this entire level your latch will be working, and during this entire level your latch is not going to work. Okay, now let's say suppose if your S is equal to 0, R is equal to 0. Now from this point to this particular point your latch is going to work since your enable signal is equal to 1. And what is your S is equal to 1? S is equal to 1, R is equal to 0 means your output will be equal to 1. So from here your output will be equal to 1 and it is becoming 0. And if you can see here S is becoming 1 at the low level. Okay, whenever your enable signal is equal to 0. So here the latch is not going to respond to whatever the inputs you are going to give whenever your enable signal is equal to 0. So that is, it is going to hold this particular signals, and let me erase this. So S is equal to 1 itself. Okay, so at this particular point S is equal to 0, R is equal to 0, which means hold condition. So Qn will not change, and up to here the Qn will not at all change. Okay, and at this particular point again your S is becoming 1, S is becoming, sorry, R is becoming 1, so your output will become 0 and it will hold its past state, and it will hold its past state up to this particular point. Up to this particular point it is going to hold its past state. So since the device is working on the levels with respect to the level of your enable signal, so that's why it is known as level sensitive device. It is sensitive to the level. The device is going to work on the levels of the circuit. Okay, and let's say suppose if your input has some noise and due to the noise we have some disturbances inside your input. Let's say suppose at the last, let me draw the diagram. We have a transitions like this. Okay, now so due to this noise transitions which are seen at the output, so this noise can be viewed at the output which are being given in the input. So your S is equal to 1 and if S is equal to 0, R is equal to 0, it will be constant only. Let me make R is equal to 1 also. R is equal to 1. Okay, now S is equal to 1, R is equal to 1, invalid state. Up to here we will get invalid, and again S is equal to 0, R is equal to 1 means it is 0, and again if it is S is equal to 1, R is equal to 1, again it's invalid. Okay, so like this, whenever there is some noise transitions, whenever there is noise and whenever your input is not stable, so this noise is also affecting your output because it is a level sensitive device and there is a lot of opportunity of your noise which can affect your output. Okay, is this clear? So this is our NAND gates. and this is going to give in here this one, and we have our AND gates which are connected over here, and this is our S and this is our R, and we have one enable signal. Now, whenever you are going to give S is equal to 0 and R is equal to 0, whenever you are going to go, let's say S is equal to 0 and R is equal to 1. That means here it will be equal to 0, S is equal to 0, and here it will be equal to R is equal to 1. Okay. Now, what is happening? Obviously, output of your input of your NAND gate is equal to 0, output will be equal to 1. And here 1, that means it will become 0. Okay. So this is acting as your active low SR latch. Okay. If you are using NAND gates and at the enable you are using AND gates, this is acting as your active low SR latch. But okay, first I will write down here. It is active low SR latch if you are giving your AND gates at your enable, okay, with your enable. But if you are giving NAND gates with your enable, it will act as active high star latch. I will draw here. So if you are using NAND gate, and one more NAND gate over here, one more NAND gate over here, and this output is given to here. So these two are connected with each other, enable, and this is S and R. Now let's take the same example. S is equal to 0, R is equal to 1. Let's say S is equal to 0 and R is equal to 1. So if any one of the input of your NAND gate is 0, then it will become 1. Okay, so here S is equal to 1. And if any one of your input of your NAND gate, okay, so here R is equal to 1 and this is 1. So 1 and 1 is nothing but 0. R is equal to 0. So here S is equal to 1 and R is equal to 0. Okay. So any one of your input of your NAND gate is equal to 0. Obviously your output is equal to 1. So this 1 will be transferred over here, and here you are going to get 0. See the difference? Previous case you are getting 1. Now here you are getting 0. So this is acting as active high SR latch. So if you are using NAND gates with your enable signal, it is acting as a active high SR latch. But if you are using AND gates with your SR latch, then it is acting as your active low SR latch. So this is the difference you should be noting. So is this clear? Any doubts or any queries here? Yes. So that's all about this session. So in tomorrow's session, we will see the diagrams of your JK latch and D latch, and we will also see how to build your T latch. And only in this particular latches, we will be seeing the diagrams and we will be analyzing the things. And once we started the flip-flops, we will be going little bit faster only, and we will see what are the excitation tables and the truth tables and what are the characteristic equations. Okay, so flip-flop conversions. So we are not going to again see the diagrams of each and every flip-flop, and only in this latches only once we will see the circuit diagrams of each and every latches. Okay, yes, so that's the agenda.